Assalamualaikum and hi everyone. Glad to see you again in this semester 2. Right, so to those who not yet subscribe my YouTube channel, so please subscribe my YouTube channel. Okay, and then don't forget to press the bell icon and you will never miss any update. Right, so for the first topic, that is chapter 1, reaction kinetic, consists of 3 subtopics. 1.1 rate law, 1.2 collision theory and transition state theory, 1.3 factors affecting reaction rate. Right, so for the first week, week 1, you are going to learn about 1.1, that is rate law. The first part, you are going to learn the definition of reaction rate, and then explain the graph of concentration against time in relation to reaction rate. Write differential rate equation. Determine the rate based on the rate differential rate equation. Define rate law, order of reaction, and half-life. Okay. First, we have to know what is the meaning by reaction kinetics. So in general, so it is about a study of rates of chemical reactions. Then it's also about the effect, these rates, and reaction mechanism by which reactions occur. Right, so in every chemical reaction that occur has its own speed at which product is formed from reactants. Okay, this rate is called reaction rate. Right, so for example, in our daily life, so wood combustion has a fast reaction rate. And then for iron rusting, it has a slow reaction rate. So we can define rate reaction is a changes in concentration of a reactant or a product with time. The unit of rate of reaction is mole per liter per second, or mole per dm cube per second, or molar per second. As for the time here, it can be per second, per minute, per hour, or per year. It depends on the question. Okay, for example, let's say I have reactant A. Okay, from reactant A decompose into product B. So we can write the rate of the reaction. Rate is equals to negative D concentration A over dt, where D concentration A is referred to the change in concentration of A. And dt is referred to the period of time or change in time. The negative sign here shows that the concentration of A will decrease with time. Okay. Alright, so for B, rate is equals to positive D concentration B over dt, where D concentration B is the change in concentration of B. Okay, as the reaction goes by, the concentration of B will increase. So that's why we write positive sign here. Okay, when we illustrate in form of graph, okay, graph of number of molecule versus time in second. So we can clearly see that molecule A, it will decrease. And then concentration B, molecule B, it will increase with time. So this is the curve for concentration B increase, and this is the curve for the concentration A decrease. What is the information that we can get from the graph of concentration of reactant against time? So let us consider for this reaction. So this is the decomposition of hydrogen peroxide. Okay, decompose into liquid water and oxygen gas. Okay, so for the rate of reaction, when refer to the hydrogen peroxide is equals to negative, as the concentration of reactant hydrogen peroxide will decrease. Okay, D concentration H2O2 over dt. Okay, when we plot the graph, we will get a curve graph here. Curve here. Right, so what are the rate that we can find out from this graph? So the first is referred to the average rate that we can be defined as the rate over a period of time. Okay, So from the graph, we can find out the average rate, the purple line. So meaning that, so you draw a line from the first point directly to the last point. So this is referred to the average rate. And then draw a tangent. Okay, draw a tangent. And then we can calculate the slope of the tangent. So the slope of the tangent is referred to the rate of direction. Okay, so negative sign here because the concentration of rectangle will decrease. So when we calculate, so we will get here, okay, 1.3 times 10 power of negative 3 molar per second. Alright, so if this is the formula for you to calculate the slope of the tangent. Right, second information that we can get from this graph is instantaneous rate of reaction. That is referred to the rate of reaction at a given time. Let's say I want to calculate the instantaneous rate, the red line at t equals to 300 seconds. So at this t, 300 seconds. So what is the instantaneous rate at this t equals to 300 seconds? Right, so you can draw a tangent, okay, a tangent that pass through this point, 300 point, at this point. Okay, next draw a tangent to find out the slope of the tangent. Okay, calculate the slope of the tangent and you find out the instantaneous rate, okay, at t equals to 300 seconds is 1.17 times 10 power of negative 3 molar per second. Okay, from the graph, we can find out the initial rate of direction. That is referred to the instantaneous rate at the beginning of direction. Which means we have to draw a tangent line. Okay, start from the initial concentration here. Okay, so draw a line. Okay, right. So next, draw a tangent. Okay, and find out the slope of the tangent. Okay, so the initial rate for this reaction is 3.57 times 10 power of negative 3 molar per second. Alright. Okay, next, rate differential equation relates the rate of this difference of reactant and the rate of appearance or formation of the product. So consider for the following reaction. So we have A, we have B produce C and D, where A, B, C, D is the stoichiometric coefficient. So we can write the rate differential equation as follows. Okay, rate is equals to negative. Alright, so the negative sign here because the concentration of reactant decrease. Okay, decrease. Alright, so 1 over A, because the coefficient here is A, so it becomes 1 over A. D concentration of A over dt is equals to negative, because concentration B will decrease. 1 over B, because coefficient for B is B. Okay, D concentration B over dt is equals to positive. Since C is the product, 1 over C, D concentration C over dt is equals to positive because D is also the products. Okay, 1 over D concentration D over dt. Okay, so please remember here, so the negative sign here to show that the concentration of reactant decrease. Okay, whereas for the positive sign here, it indicates the concentration of the product increase with time. Okay, for example, so formation of ammonia. So nitrogen gas react with 3 mole of hydrogen gas to produce 2 mole of ammonia. So the differential rate equation is rate equals to negative D concentration and 2 over dt is equals to negative 1 over 3 because coefficient for hydrogen is 3, so 1 over 3. D concentration H2 over dt So remember, negative sign here because the concentration of reactant decrease with time. Is equals to positive 1/2 because coefficient of ammonia is 2, D concentration NH3 over dt. So the positive sign here because the concentration of ammonia will increase with time. So let's say the value of the rate here is 0.1 molar per second. Right, so what is the equation mean? So we can find out the information from this equation. 3 information. So the first one, the rate of disappearance of N2 is 0.1. Okay, because coefficient here is 1. Okay. However, the rate of disappearance of H2 is 3 times faster than rate of disappearance of N2. That is 3 times 0.1 molar per second. Okay. Alright. Okay. And then for the rate of formation of ammonia is 2 times fast. Okay. That is 2 times 0.1. Alright. So example 1. Consider the reaction. So we have 2 Hi gas produce H2 gas and I2 gas. And then you have to write the rate expression for the reaction. So rate expression here means rate differential equation. So here is the sample answer. Alright. So first you have to write the title. The title here is referred to the rate equal to. So negative means concentration of the reactant will decrease 1/2 because the coefficient of Hi is 2. D concentration Hi over dt is equals to positive D concentration H2 over dt. Positive sign here because hydrogen gas is the products. Okay, and product will increase with time. So positive sign. So same thing goes to I2, positive D, concentration I2 over dt. Because I2 also the product. Product will increase. So this is what we call rate differential equation or rate expression. Right, so second question, determine the rate of the disappearance of Hi when the rate of I2 formation is 1.8 times 10 power negative 6 molar per second. Alright, so given to in the question is the value 1.8 times 10 power negative 6 value for this expression. Okay, right, so including the positive sign. Right, so we want to find out the rate of disappearance for the Hi. Okay, right. So relate these two expressions. Okay, substitute the values. However, rate of disappearance of Hi is referred to the D concentration Hi over dt without 1/2. So you have to bring 1/2 to the other side. Okay, and become like this. Okay, so negative sign remain in this side, at the left side. So 1/2 bring to the other side and become 2 times 1.8 times 10 power negative 6 molar per second. And this is the values of the rate of disappearance of Hi with the unit. Okay, and remember rate is always positive value. Okay. Right. Okay. So the sign here should be in front of the expression. Okay. Whether positive sign or negative sign. Okay. Okay. For example, number 2. Okay. For this reaction, so consider this equation. Nitrogen gas was found at a rate of 0.72 mol per liter per second. Calculate the rate of water formation, oxygen consumption, and ammonia disappearance. So we take a look at A. So first of all, you have to write the rate differential like this. Okay. Alright, so remember you have to write the title which refer to rate. And then for the reactant will decrease. So you have to write negative sign. Coefficient become 1/. As for the product, the sign should be positive sign. Coefficient become 1/. In the question, it's already given the information about the rate of the formation of nitrogen, which refer to 0.72. So remember, 0.72 is referring to the expression of d concentration N2 over dt. Means that it not include the value of 1 over 2. Okay, only this expression. Okay, and then we want to calculate the water formation. So relate expression for nitrogen with water. Okay, we get like this, right? And then we want to find out the rate of formation, which refer to this expression d H2O, d concentration H2O over dt only. So therefore, 1 over 2, you have to move to the other side and become like this. Okay, remember the sign should be in front of the expression. Alright, so 1 over 6, bring to the other side, become 6 times half times 0.72. Okay, and you will get rate of the water formation is 2.16 mole per liter per second. Alright, next, oxygen consumption, which means rate of oxygen disappearance. Okay, so compare expression for nitrogen with expression for oxygen. So, alright, so we'll get like this. Okay, so we want to find out the rate of consumption of oxygen gas, which means for this expression. Okay, so meaning that 1 over 3, you have to move to the other side and become like this. Okay, 1 over 3, move to the other side, become 3 times 1 over 2 times 0.72. And the sign should be remain in front of the expression. Okay, so we get the rate of consumption of oxygen is 1.08. Okay, mole per liter per second. Alright, next, we want to calculate the disappearance of nitrogen gas. Right, so relate expression for nitrogen with ammonia gas. Okay, what we want to find out is only this expression, d concentration and H3 over dt. So therefore, you have to bring 1 over 4 to the other side and become like this. And we get 4 times half times 0.72. Okay, the rate of ammonia disappearance is 1.44 mole per liter per second. Alright, so now we move to the rate law, or also known as rate equation. So it can be defined that rate law can be defined as the relationship of the rate of reaction to the rate constant and the concentration of the reactant raised to some power. So let us consider for this following equation, right? Alright, so rate is directly proportional to the concentration of the reactant only. Only the reactant. Okay? Right. So when we want to change from directly proportional to equal to, so we have to add a constant. Okay, so we add a constant k here. So rate is equal to k concentration A power of x times concentration B power of y. So both is referred to the reactant only. Alright, so what is k? K is referred to the rate constant, and x power of x here is referred to the reaction order with respect to A. And what is y? Y is referred to the reaction order of y with respect to B. Okay, when we total up, the overall reaction order is x plus y. Okay, order of reaction. So is the power of reactant's concentration in the rate law, which define how the rate is affected by the reactant concentration. So this is the previous example. Okay, where x here is referred to the reaction order or with respect to A. Okay, and y is referred to the order of reaction with respect to B. And the overall order is x plus y. Alright, so x and y here usually is generally small, positive. It can be positive or negative integers. Alright, so and then can only be determined experimentally. Okay, experimentally. Right, and then always define in terms of concentration of the reactants. So which means it's refer to the concentration of reactants only. And it is not related to the stoichiometric coefficient. So for example, okay, so for this one, for this equation, the rate law is equals to K concentration F2 times concentration ClO2 power of 1. So power of 1 here is not related to the stoichiometric. Okay, so the value of order here is depend on the experiment. Okay, experiment data. Alright, so for example, let's us consider the reaction A decomposed to produce product. Then we'll get the rate law is equals to K concentration A power of X. So if X is equal to 0, right, so we get rate is equals to K concentration A power of 0. Let's assume that the initial concentration of A is 1.0 molar. Okay, so therefore we'll get rate 1 is equals to K times 1 power of 0 is equals to K. Anything power of 0 is equals to 1. Okay, that's why rate 1 is equals to K. Let's say we double the concentration A, okay, from 1 molar to 2 molar. What would happen? Okay. Right, so we substitute into the rate law. Rate 2 equal to K times 2 power of 0. Okay, so we'll get rate 2 equals to K, which refer to rate 1. What can we interpret from here? So we can conclude that the rate is not depend on the concentration of A. Okay, so therefore, the order of the reaction with respect to A is 0 order. Okay, right, so if X is equals to 1, so we get rate equal to K concentration A power of 1. So we assume initial concentration of A is 1.0 molar. So we know that rate 1 equals to K times 1. Right, so what would happen if concentration A is double from 1 molar to 2.0 molar? So we substitute in the rate law, we will get rate 2 equals to K times 2. Right, and then we get rate 2 actually is equals to 2K concentration A. K times 1 here is refer to the rate 1. Okay. Right, so we get here rate 2 is equals to 2 times rate 1. So what can we imply here? So double the A will double the rate of reaction. Okay, so this is the direction order is first order with respect to A. Right, so what would happen if X is equals to 2? So we get rate law is equals to K concentration A power of 2. So let's say the initial concentration is 1 molar and we'll get rate is equal to K 1 power of 2. Okay, what will happen if A is double from 1 to 2 molar? So rate 2 equals to K times 2 power of 2. Then we get rate 2 equals to K times 4. Okay, right, so we rearrange rate 1. Okay, and then doubling the concentration A, the rate will increase by factor of 4. Fourfold. Okay, or also known, or you can write quadruple. Okay, so the order of reaction with respect to A is the second order. Alright, so now we move to example number 3. Write rate law for this equation. So A react with B produce C. So when A is increased 3 times, rate increases 3 times, and increasing of B, concentration of B 3 times causes the rate to increase 9 times. So from here we can get the clue here, increase concentration A increase 3 times, rate increase 3 times. So meaning that directly proportional. So therefore the order of the concentration of A should be first order. Alright, so increasing of B 3 times cause the rate to increase 9 times. Alright, so therefore this means this is referred to the second order. So you will get answer like this. Don't forget to write the title rate is equals to K concentration of A power of 1 times concentration of B power of 2. Right, so for B, reducing A by half has no effect on the rate, but reducing B by half cause the rate to be half. Okay, half and half. So therefore, concentration A is 0 order, whereas for B is first order. Answer like this. Rate equals to K concentration of A power of 0 times concentration B power of 1. Right, so now we move to the half-life. Right, so what is the meaning by half-life? Or the symbol here is T half. So half-life is the time required for the concentration of a reactant to decrease to half of its initial value. Right, for example, let's say I have a beaker containing HCl solution and the initial concentration here is 5 molar. So half-life is referring to the time taken, right? Time taken for the concentration of HCl, okay, to decrease to become half. Okay, from 5 molar become half to 2.5 molar. Okay, the time taken is what we call half-life. Okay, so this is referred to the first half-life. Okay, and then from 2.5 molar of HCl, when the concentration is reduced to half of it, so become 1.25 molar. So the time taken is referring to the second half-life. So remember, half-life is referred to the time required for the concentration of reactant to decrease to half of its initial value.